This brings us to the final part of the lab, which is the conclusion. So what is really the purpose of the conclusion? The conclusion really is just trying to bring the entire lab together, okay? We're going to summarize the results, and we're also going to talk about issues and things really moving forward, okay? So really just taking a step back and looking at the lab as a whole. So parts of the conclusion. The first part of the conclusion is going to be the introduction. We've talked about this some before, but this is a spot where you might feel like you're being redundant. Don't worry, you're not. Okay? It's great to start the conclusion by once again reminding the reader of the purpose of the lab. Okay? The next thing you're going to do is basically summarize the two bigger sections that you've already written, the procedure and the analysis. All right? You are not trying to rewrite the whole thing. This is a brief 1 to 2 sentence summary. If someone reading your lab wants a little bit more detail, they can go to the procedure, they can go to the analysis section and get that. But very, very quick overview, none of the really nitty-gritty details, just the big ideas if you're talking about the analysis, or the basic process for doing the lab if you're talking about the summary of the procedure. Once you kind of summarize what you've done so far, the new piece of information that you're going to have in this conclusion is the sources of error. Whenever we do a lab, we want to acknowledge the things in the lab that led to our results being less than perfect. We've talked about this before. No matter what, and the pullback car lab was an example of a lot of sources of error and a lot of uncertainty, but no matter what we do, we are never going to get 100% perfect result. So we want to acknowledge the things in the lab that affected those results, all the major sources of error. All right. We want to make sure, though, that we're identifying errors and not mistakes, and we'll talk about that a little bit on the next slide, what the difference is. When you're doing this, okay, get away from saying human error. In fact, you shouldn't even write those two words anywhere in your lab report, solely because it is not specific enough. Human error is a cop-out answer. And while there may be things in the lab that humans did that affected it, the biggest one I can think of is reaction time, if you're timing something, but there are others. So there might be things, errors caused by humans, but just stating human error is not specific enough. It makes my blood boil and I cringe, and it makes me want to print out your lab report solely so I can rip it up into shreds. Don't do that, okay? Be specific about the errors. If it was a timing error, then state that. State that human reaction time had an issue or had a role in the sources of error, but don't just say human error. It's not specific enough. The other thing you want to do, and we'll work some more on this throughout the year, not as much in the beginning, but we want to think about how those sources of error affect the results. And what I mean by that is, do the errors lead to an increase in the numbers? Do they lead to a decrease? Is it a random change? All right. Well, sometimes you'll hear the term systemic errors. Those are ones that lead to a consistent increase or decrease in your data. All right. So maybe there's something that's slowing down a car as it's sliding down a ramp. Okay. That might lead to you actually consistently measuring the velocity slower than what it should have been. That would be an example of a systemic error. A random error is one, though, where there's no consistent pattern, that it's always making it bigger or smaller. It's random, hence the name. All right, so let's talk for a second about the difference between sources of errors and mistakes, because we don't want to identify mistakes that we made in the lab. We want to identify sources of error. The biggest difference that I can think of, or the biggest way I can, or the easiest way I can put it, is that sources of error are things that could not be fixed. You cannot help that there's human reaction time. You cannot reasonably help in a lot of these labs when there's air resistance or friction or many, many other things. Things that you really have no reasonable control over are sources of error. You can't help that there's always uncertainty in every single measurement. That's not something that you really have the power to easily fix. Mistakes, on the other hand, are things that could have been fixed easily and should have been fixed. Things like making a mistake in your calculator and having to recalculate something, measuring something wrong. Maybe you accidentally measured in inches and you meant to measure in centimeters. That's a mistake, ladies and gentlemen, and that is something that could be fixed and should have already been fixed, but it's not a source of error. I have a few examples here of the difference. Major sources of error: uncertainty in measurement. That's a big one that's almost always present. Uncertainty in the equipment. Pullback car is a perfect example of something that doesn't behave the same way every single time. You really can't help that. That absolutely is a source of error. Another one is sometimes we'll make assumptions that aren't always true. Like we might assume that a surface is frictionless and there actually is friction. That would be a source of error. It's okay, but we do want to recognize it. Things that are mistakes and are not sources of error and should not appear in this section: incorrect calculations, measurements, things like that. Issues with the equipment: maybe you had to get a new pullback car. That doesn't make it a source of error. It's really not a mistake necessarily on your part, but something that could have been fixed. Your lab partner or me, I am not a source of error, nor is your lab partner. Okay, so even if you think that we messed you up and ruined your results, we're still not sources of error. And the last thing we want to talk about is future research. So research is not done in isolation. Science is not done in isolation. We're always doing one research project that leads to another or is linked to another or maybe is in collaboration with another project and the two support each other. So the last thing we really want to do is we want to provide a little bit of that bridge. Okay? Think about how we either could have changed something about the lab to improve upon it, get better, more precise results, or maybe just get more information, get a more complete picture, or what would be a direction for further research. So what's something new we could do that links to whatever the purpose of the lab was, and is going to further broaden our understanding of science. So a few common pitfalls here that we'll talk about, and then we'll look at a sample. Number one, do not include opinions or speculations. Okay, everything should be backed with evidence, backed with data. It should never be what you think. It should be what you know and can prove from the lab. All right. Do not make conclusions without backing them with evidence. That actually is more in the analysis section, but same idea. We don't want to back things with our opinions. We want to back them with evidence. When we're doing the conclusion, do not rewrite the entire procedure, nor should you rewrite all of your data. Okay? Make sure that you are just being concise in the conclusion. 1 or 2 sentences and move on. So we have an example here of a good conclusion. I'm just going to point out a few parts here. We start here with a restatement of the purpose. All right, that is the first thing. Yes, it might feel redundant because we've already talked about it before, but that's a great place to start. Here is the recap of the procedure. Okay, simply 2 sentences. You notice we're missing some of the gritty details, but 2 basic sentences explaining the general idea of what we did. We now have our recap, or we then have a recap of the analysis. All right. Again, just really the big idea is really the concluding statements. As the length of the pendulum increases, so does the period of oscillation. All right. And then we get into, again, this part that's a little bit more specific than what we're concerned with now, but we'll get there a little bit later on in the year. Then we finish with sources of error. All right, so errors in the measurement of the length. Sometimes you can also use this word, uncertainty, same idea, in the measurement of the length and the angle. Another source of error was the assumption the pendulum was a simple pendulum. This is getting a little bit ahead of ourselves content-wise, but that was an assumption we made in the lab, and that affected the results. It wasn't completely true, but we were basically willing to accept that it was close enough. All right, but we want to make sure that we're aware of that and we identify that. Okay, and lastly, we have this link to further research, just a 1-sentence statement. This could be repeated to test the effects of other variables. So now we're thinking about how we could extend this using the same basic idea, studying in this case a pendulum, but extending it some, showing that this research is going to continue, showing this research is not done in isolation.